There are several other unconventional fossil fuels that are even more unusual than the shale gas and tight oil that we've been talking about. This class of unconventional fossil fuels requires converting the extracted material into crude oil, a process that is very costly and energy intensive. These conversions require specialized processing plants compared to conventional fossil fuels. These fuels are called synfuels and include oil and gas produced from coal, tar sands, and oil shale. Of these, tar sands are the most economically viable and most widely used at present. So let's talk about those. Tar sands, sometimes called oil sands, form when oil moving upward within a reservoir of porous and permeable sand is not stopped by an impermeable sedimentary layer. Oil begins to escape from the sand at the surface and is biodegraded by oil-producing bacteria, causing the oil to become highly viscous asphalt or tar called bitumen. The world's largest exploited deposit of tar sands is in northern Alberta. Tar sands can be mined and processed with hot water to separate the bitumen from the sand. The steps in this process are shown in the bottom right figure. Let's go into it a little bit more. A lot of energy and water resources and processing go into extraction of synthetic oil from the tar sands. Some heavy oils are too viscous to be extracted directly by pumping. About 60% of the oil extracted from the tar sands is stripped by surface mining, and for this, 2 barrels of water are needed for every barrel of oil produced. This mining process generates tailings that are a mixture of water, mineral residue, and unrecovered bitumen, and can leach toxic materials into surface and groundwater supplies. Another 40% of tar sands oil is from steam injection, in which steam is injected into a well, lowering the oil's viscosity in the surrounding deposits. The thinner oil is then pumped until resistance again becomes too great, at which point the process is repeated. Another method shown on this slide involves a dedicated injection well surrounded by 4 pumping wells. Here, steam is injected continuously while the pumping wells remain in full production. Of course, this injection of steam requires large amounts of water as well. Both processes are extremely energy intensive when transport, processing, steam injection, and cleaning are considered together. Finally, oil shale is a sedimentary rock containing kerogen that has not been heated enough within the earth to change the kerogen into hydrocarbons. Oil shale can be mined, but it must be subjected to a high temperature before petroleum-like liquids can be separated from the rock. Over 60% of the world's reserves of oil shales are in the Rocky Mountains. Important environmental issues remain and may limit production, such as the region's limited water supplies and concerns over increased carbon dioxide emissions. The original method of processing oil shale involved mining and crushing the rock and then heating it. New methods, such as heating the rock in place, seek to avoid disposing of large volumes of waste rock. Both methods are so energy intensive that the production of oil shale is not currently economical. The heating method is shown in the figure here. Something that's a little bit different is methane hydrate. In the 1970s, surveys of the seafloor turned up large methane hydrate deposits. More recent deposits have been found near polar regions. From a material properties perspective, these materials are unique and quite amazing. A clathrate is a chemical compound in which molecules of one material, the host, form a solid lattice that encloses molecules of another material, the guest. Methane hydrate is a naturally occurring clathrate in which a host lattice of water ice encloses guest molecules of methane. 1 cubic foot of solid methane hydrate will release about 164 cubic feet of methane gas. The primary reason commercial production is not yet taking place is the high potential for the uncontrolled release of gas, which is flammable, as shown here, and is a potent greenhouse gas. As we evaluate the various fossil fuel energy sources that the world has available, we can consider them in terms of energy return on energy investment. This ratio tells us how much energy we get out versus how much energy goes into the production of that fuel, including extraction and refining. The larger the energy return on energy investment, or EROI, the more efficient and usually economical the fuel source is. If energy return on investment is less than 1, then it takes more energy than you get out, and it's not practical to use it. If energy return on investment is less than 3, it may be minimally useful over extended periods. Of the fossil fuels, coal has the highest EROI in the range of 40 to 80 to 1. Conventional oil and natural gas in the US both have an EROI of about 18 to 1. These conventional fossil fuels require the least intensive extraction and processing methods. Shale gas is about 12 to 1, while tight oil is about 7 to 1, and tar sands are about 5 to 1, because these fuels require greater energy for extraction and processing. Oil shale is about 3 to 1, and right now methane hydrate is less than 2 to 1, which explains why these resources aren't economical to use. It's important to note that the trend for conventional fossil fuels is decreasing EROI over time as the easiest deposits are extracted and depleted. We might expect a similar trend for shale gas, tight oil, and tar sands unless there are significant further technological developments while large amounts of these resources remain.